Wow, thank you very much. Applause at the beginning. That's great. Yeah, so I'm going to talk. So I'll talk about testing fundamental physics using laser-cooled molecules. And let me just jump straight in here to the first topic that I have for you, which is using molecules to search for varying fundamental constants. And now, actually, when you hear about this topic for the first time, it seems kind of funny because you think of the fundamental constants as being constant. But actually, in many new theories of physics, the constants are not really supposed to be constant at all. They enter as parameters of these theories, and they are allowed to vary, and indeed expected to vary. So, for example, unification theories, theories that try to unify gravity with the other forces, they tend to predict that the fundamental constants will vary in space or in time. And some theories of dark matter, in particular ultralight dark matter, they predict that the fundamental constants may oscillate in time. And some theories of dark energy predict that the fundamental constants will depend on the local matter density. So that if I measure the fundamental constant here on Earth, where the local matter density is very high, I could expect to get a different value to if I measure it out in outer space, where the matter density is very low. And so you see actually these three things here. What have we got? We've got, quantum gravity, dark matter, dark energy. These are three of the biggest unsolved problems that we have in fundamental physics. And it seems that varying fundamental constants can potentially tell us something about all three. How could we do it? Well, the best way to do it is to measure the transition frequencies in atoms and molecules over time and space and to see whether they're varying in time and space. The electronic transitions in atoms are mainly sensitive to the fine structure constant. And indeed, the best measurements of variation of the fine structure constant all come from atomic clock measurements. The vibrational and rotational transitions in molecules, they are sensitive to the electron-to-proton mass ratio, ME/NP. And this is a sensitivity that atoms do not have, but the molecules do have. And so the molecules have an advantage here. Okay, so to make really precise measurements of the variations in this quantity, ME/NP, we would like to build a molecule clock. It's similar to an atomic clock. And if we do that, building a clock that is based on the vibrational transitions of a molecule, this will then also serve as a frequency standard in the mid-infrared, which could be very useful because that's a part of the spectrum where currently we have no good frequency standards. So the system that I'd like to advocate is ultra-cold calcium fluoride molecules in an optical lattice. Here is the energy level structure that's relevant here. And the proposal is to build a clock that is based on the fundamental vibrational frequency of the molecule, which is a transition at 17.5 terahertz. We would like to measure this by driving this Raman transition. This vibrational frequency, it scales as the square root of the electron-to-proton mass ratio. The line width of this transition is expected to be about 5 hertz. So should make quite a good clock. The molecules will be in the lattice, so the Doppler shifts are eliminated. And then an important point, in this Raman transition here, you see the way I set it up, the rotational state is not changing. Okay, in fact, the only thing that changes is the vibrational state of the molecule. And it turns out that if all you do is change the vibrational state of the molecule, then actually hardly anything changes. Okay, none of the properties of the molecule change. In particular, the magnetic moment is hardly changed and the DC polarizability is hardly changed. And so the Zeeman and Stark shifts, they cancel the high accuracy. What's more, we can also measure this rotational frequency here. It's at 20 gigahertz. This rotational transition is, in fact, very sensitive to electric fields and magnetic fields. So you can use the rotational frequency to determine the fields in the experiment and thereby determine the residual Zeeman and Stark shifts in the clock frequency. So for all these reasons, we think this will make a very interesting clock. And this is the system that we're trying to use. I should also mention here some beautiful work on a molecular lattice clock in Tanya Zelevinsky's group using strontium-2 molecules, which is closely related to what I'm talking about. Now, I spoke about the cancellation of the Zeeman shifts and the DC Stark shifts. We, of course, also have to worry about the AC Stark shifts. Okay, the molecules are sitting in the high-intensity antinodes of the light field here. And so we have AC Stark shifts, which in general are a big problem for the clock. So we need to find some magic wavelengths where the AC polarizability of the two vibrational states are equal, okay, so that there's no AC Stark shift of the clock frequency. So the thing we care about then is the differential polarizability of these two vibrational states. And here's a calculation of the differential polarizability as a function of the wavelength of the light. You see all kinds of structure, but importantly, there are some places where the differential polarizability crosses zero. These are the magic wavelengths. And if you operate the lattice at one of these wavelengths, then the clock frequency will be independent of the lattice. And I draw your attention in particular to this magic wavelength out here near 700 nanometers, where the differential polarizability crosses zero at a very shallow angle. Again, that we think is particularly attractive. So you can go ahead and try to calculate what you think the fractional instability of the clock is. This is basically the precision of the clock as a function of the averaging time here, and we find for reasonable parameters that in an averaging time of about 10 to the 4 seconds, we would expect to reach close to parting 10 to the 17. We've also tried to estimate the accuracy of the clock by evaluating the systematic uncertainties that we would expect for some typical laboratory conditions here. And again, here we're anticipating that we could reach an accuracy for the clock close to 1 part in 10 to the 17. So this actually looks like a very interesting kind of clock. All right, now I'm the first, I think, person in this meeting to talk about laser-cooled molecules. So I'll just say a little bit about the experimental methods that we use to get the molecules trapped. So we have an apparatus, something like this. We make our calcium fluoride molecules in a beam using cryogenic buffer gas cooling. Then we apply two-dimensional transverse cooling to the molecular beam in order to collimate it. Then we slow the beam down to low velocity using the radiation pressure of this counter-propagating laser light, and finally capture the molecules in the magneto-optical trap. Here's a little bit of data showing the velocity distribution of the molecular beam measured for the molecules as they arrive at the MOT here. The black curve is the velocity distribution we get when we just do nothing. So that's the distribution straight out of the cryogenic buffer gas source here. It's centered, in this case, around 140 meters per second. And the red curve is the velocity distribution we see when we apply this counter-propagating slowing laser light. And in this particular case, the frequencies of the slowing laser are tuned, so the molecules moving at this speed, it's about 180 meters per second, are Doppler shifted into resonance with the light. And you see they slow down to about 100 meters per second. And they also bunch up at this particular speed. That's because by the time they reach 100 meters per second, they've Doppler shifted out of resonance with the light, and so they will tend to bunch up at this speed. Okay, and then we apply a frequency chirp to the light to follow this changing Doppler shift. And as we increase the frequency chirp, we can push the molecules down to lower velocity. Then eventually, when we tune everything up just right, we get the molecules down to about 10 meters per second, which is slow enough for them to be captured in the magneto-optical trap. The MOT uses 4 wavelengths, 4 lasers to address the 4 lowest lying vibrational states of the molecule here. And we take pictures of the trapped molecules, take pictures of their laser-induced fluorescence. Here is a picture taken actually with a regular mobile phone camera, just looking through the vacuum viewport, and you see this little orange blob here. That's our MOT, calcium fluoride. This particular one contains about 5 times 10 to the 4 molecules, and the density is 5 times 10 to the 6 per cubic centimeter. We don't normally use a mobile phone camera. Normally we use a nice CCD camera. We measure the temperature of the molecules using the usual ballistic expansion method. Here is the temperature coming down during the very final stages of the cooling process here. So we actually capture the molecules in the MOT, and then we apply 2 phases of subdoppler cooling to bring the temperature down. This is the very last stage of the cooling when we reach a temperature of about 5 microns. At that point, we can transfer the molecules into an optical lattice. Now, I spoke already about these magic wavelength lattices. Ultimately, that's what we would like to use for the clock experiment. To begin with, we're doing a simpler thing, which is to use a 1064 nanometer lattice. That's nice because we have 50 watts available. We send the light through the vacuum chamber, retroreflected to make a standing wave, and the molecules are trapped around the antinodes of the standing wave. There's a picture showing the calcium fluoride molecules trapped inside the optical lattice. And here we have about 500 molecules at 50 microkelvin. The lifetime in the lattice is about 1.7 seconds. And the molecules are cooled into the lattice, which increases their density. So here we have a density about 4 times 10 to the 9 per cubic centimeter. Right now, the number of molecules in the lattice is relatively small, a few hundred. But actually, just recently, the Giller group, Junier group in Giller, and the Dave DeMille group in Chicago have both demonstrated a blue detuned Mott method that hugely increases the efficiency of coupling into optical traps. And they're trying to implement that also. We're really expecting to once we do that, to have many thousands of molecules in the lattice. Okay, so the molecules are in the lattice, then we're ready to start driving transitions in the molecules. Here's an example where we drive the rotational transition of the molecule. And it's a transition in the microwave domain at 20.5 gigahertz here. And we see these beautiful Rabi oscillations for molecules that are trapped inside the lattice. Here we're driving the rotational transition. For the clock, what we really would like to do is to drive this vibrational transition. And we're interested in doing that in 2 different ways. First, to just drive the transition directly, and secondly, driving this Raman transition that I spoke about. So I'll just tell you a little bit first about driving one-photon transitions, driving transitions directly. I remind you, this is a transition at 17.5 terahertz. As a wavelength, it turns out 17 terahertz is 17 microns. Okay, so we need a 17 micron laser to drive this transition directly. And, we're actually able to obtain a custom-built quantum cascade laser operating at 17 microns to be able to drive this. So here's some recent data, still quite preliminary, showing that indeed with this interesting quantum cascade laser we can drive directly this vibrational transition of the molecule. What you're seeing here is the hyperfine components of this vibrational transition. Actually, as far as I know, this is probably the first laser spectroscopy in this part of the electromagnetic spectrum. It caused a great deal of difficulty. One difficulty we had is, well, how do you know the frequency of your 17 micron laser? Okay, there are no wave meters available. So how do you know the frequency that it's running at? To solve that, we actually had to do some absorption spectroscopy of N2O. Okay, N2O, that's laughing gas. Yeah. And it turns out that the bending mode of the N2O molecule has transitions in exactly this region. The strong lines here, the really intense lines, had actually been measured previously at NIST. And so they're able to use those strong lines to calibrate the frequency of the laser and thereby scan the correct spectral region. So the red data here is our measurement of the absorption spectrum of N2O. The blue lines are a model. And actually, we measured hundreds of lines in the spectrum of N2O. Now, we had to do this initially to calibrate the frequency of the laser. Of course, what we'd really like to do now is turn this whole thing around. Okay, we're going to measure, hopefully, the frequency of these calcium fluoride transitions to very high accuracy. And once we've done that, we can actually transfer that accuracy back onto the N2O lines, where there are hundreds of lines. And that we think will actually be very useful for other people. It's much easier to do the spectroscopy of a tube of laughing gas compared to doing spectroscopy of ultracold calcium fluoride. So these are single photon transitions. And I should say, so I don't mislead you, this scan at the top here is 500 times narrower. For the clock, what we'd really like to do is to drive these Raman transitions. And our plan to do that is to drive the up leg at 1064 nanometers. That's already our lattice laser. And then the down leg at 1134 nanometers. We're expecting this transition, of course, to be very narrow. And so the lasers have to have very narrow line widths. Right now in the lab, we're just putting the final touches to the frequency locks. So we're locking both of the Raman lasers here to an ultra-stable cavity with a finesse of 300,000. That work is almost complete, and we're gearing up to measure these Raman transitions for the first time. In the longer term, what we'd really like to do is to compare two different clocks. Okay, actually, I didn't say it, but of course, if you want to measure the variation of the fundamental constants, you can't do it using a single clock. Okay, you need two different clocks. Ideally, what you have is our vibrational clock, our molecule clock, which is sensitive to the electron-to-proton mass ratio, and an atomic clock, such as a strontium lattice clock, which is not sensitive to the electron-to-proton mass ratio. And then it's the frequency ratio of these two clocks that you want to study to see whether that is varied over time. And that can be done with the help of an optical frequency comb. I'm starting to look now, looking into the longer term, how we could actually make this frequency comparison between a molecule clock at Imperial College and a strontium lattice clock at the National Physical Laboratory, which is not so far from us. All right, so now I'm going to switch to a different but related topic, which is using molecules to measure the electron's electric dipole moment. And I'll start here with a little bit of motivation. Here is a graph which shows you the predicted value of the electron's electric dipole moment according to various theories. The standard model of particle physics says that this electron EDM should be incredibly tiny, about 10 to the minus 40 e-centimeter. Whereas most high energy theories that extend the standard model, they all tend to predict much, much larger values for the electron EDM, many orders of magnitude larger. So, for example, this green box here is the minimal supersymmetric extension of the standard model. The blue box is other forms of supersymmetry. The dashed line here is the current experimental limit, which comes from a really beautiful experiment using trapped molecular ions completed at Gila, which Luke Pullman is going to speak about later this morning. EDM measurements are spin precession measurements. So here I have a particle that has a spin, and associated with the spin, it has a magnetic dipole moment. And if I put this particle in an applied magnetic field, then there will be a torque due to the interaction of the magnetic dipole moment with the applied magnetic field, and that torque causes the spin to precess around the direction of the magnetic field. And now my particle here has a slightly non-spherical charge distribution. That's telling you that it has an electric dipole moment. So if in addition to the magnetic field, I also apply an electric field, then there will be an additional torque due to the additional interaction of the electric dipole moment with the applied electric field. And that extra torque will cause the spin precession frequency to change as it speeds up a little bit. And then conversely, if I put the electric field in the opposite direction, the torque will be in the other direction, and the spin precession frequency will slow down. So in fact, all you have to do to measure the electric dipole moment of a fundamental particle is to measure the change in the precession rate when the electric field direction is reversed. Indeed, all EDM experiments of all fundamental particles are done that way. In order to make this experiment maximally sensitive, you would like to apply a very large electric field. And a really good way to apply a big electric field is to use an electron that is bound up inside a molecule. So the cartoon is supposed to show you here. The idea is that in the lab, we apply a rather modest electric field, which does the job of aligning the molecule in the lab. And then the valence electron of the molecule has access to the full internal electric field of the molecule along the bond here, okay, which is absolutely enormous compared to the field that you can apply yourself in the lab. So the sensitivity is enhanced enormously for electrons in heavy polar molecules. And now the word heavy is important here. This very large effective electric field is actually a relativistic enhancement effect. Okay, and so you need highly relativistic systems, so you need heavy polar molecules. The particular heavy polar molecule that we like to use is a terbium fluoride, and we have actually built 2 experiments to use laser-cooled terbium fluoride to measure the electron's electric dipole moment. One which uses a laser-cooled molecular beam, and another one which is looking a bit further into the future, where we plan to use molecules in an optical lattice. And we have here a poster about the beam experiment. I'll just say a little bit about the lattice experiment. We're excited about these experiments, and the excitement is kind of summarized by this dashed line that I've added here. So if you take 10 to the 4 YBF molecules, which we think we can do, in a lattice with a spin precession time of 4 seconds, and you take 1,000 hours of data, then the statistical sensitivity you would expect to reach is given by this dashed line. Okay, so I'll just say a little bit about what we're doing towards a CDM experiment using YBF molecules in a lattice. The setup of the experiment, the plan for the experiment, is basically exactly the same as what I showed you already for the calcium fluoride. Okay, we try to capture these molecules in a magneto-optical trap and then transfer them into an optical lattice, and we do the spin precession measurement in the lattice. The YBF molecules are much harder to cool than calcium fluoride. So they're a lot heavier than calcium fluoride. That means it's more difficult to push them around using photons. And also the vibrational branching ratios are not so favorable for this molecule. So it's a lot more difficult, but we're making good progress. And I'll just show you some of the things that we've been doing. One thing that was really important to us was to start out with a very, very slow molecular beam. Okay? Because it's very hard to slow these molecules down, we wanted to make a cryogenic buffer gas beam that was very, very slow to begin with. Our usual beams are moving about 150 meters per second, coming out of a buffer gas source at 4 Kelvin. We've now cooled the buffer gas source down to 1.8 Kelvin, and that shifts the velocity to about 80 meters per second. And we also use this Harvard trick of using a 2-stage cryogenic buffer gas source instead of a 1-stage source. I won't go into the details here, but the upshot is this blue velocity distribution here, where we have a really significant flux of molecules all the way down to 30 meters per second. So that's a very nice starting point. Then we take these slow molecules and we apply transverse laser cooling to the molecules to collimate the molecular beam. I'll show you some results here. So what I'm showing you is the density distribution of the molecular beam, which we measure by laser-induced fluorescence detection, just using a cross pair of probe lasers. And now when we do nothing, when there's no cooling, the molecular beam is just completely filling the plane of the screen here, and we just see a cross of fluorescence which just corresponds to where the probe lasers happen to be. And now we apply the laser cooling, first of all, in one dimension, and you see this bright stripe due to molecules that have been cooled in that direction. And then we apply the cooling in both transverse directions, and we see this very bright spot in the middle here. It has about 1 million ultracold molecules per shot in the beam. And the laser cooling has increased the beam brightness by at least a factor of 300. Molecules are cooled to below 50 microcalories. Okay, so the cooling is working, and then the next step here is this laser slowing. And here I show some fairly recent data that shows that indeed we can slow down these terbium fluoride molecules. It's the change in velocity here as a function of the time that we spend slowing them. And we see a relatively small reduction in the velocity, but well, going in the right direction. And then finally, we need to capture these slow molecules in the magneto-optical trap. The mod is built. In fact, last Friday, we even had a first search to see if we could see our very first MOTS of the terbium fluoride. Well, we couldn't, but at least we're trying. Another thing that we've actually been working a lot on is the spectroscopy of these terbium fluoride molecules. Okay, so it turns out to be a relatively complicated diatomic molecule. In particular, the terbium fluoride has these low-lying electronic states here that are arising from from inner shell excitation of the 4f electrons. Okay, so you can excite a 4f electron, and this results in low-lying electronic states. We call them the 4f Hall states. And it turns out, we think, that there are small but significant leaks into these 4f Hall states. That's a big problem for the laser cooling. And in particular, it's a big problem because nobody knew anything at all about these 4f Hall states in this molecule. So we've been doing, actually, we have a nice collaboration with the Fritz Haber Institute in Berlin to do the spectroscopy to understand, well, where these 4f Hall states are. That's the first question, and what their nature is and so on. And that's actually going very nicely. We're learning a lot about this. All right, so that's a kind of summary of where we're up to on these YBF molecules. And my time is up, so let me thank the group members who've been working on these experiments. I'll highlight that we have postdoc positions available in the group, so if you're interested in working on some of these experiments, please come and talk to me. And finally, one last advert. The International Conference on Atomic Physics will be held in July in 2024 at Imperial College in London. And you're all invited. Thank you.
We have time for questions.
Great talk, Mike. I have a question about this very cold YBF source. There's this huge enhancement also in amplitude, not just the reduction in velocity. How much of that is actually the population of the respective states, and how much is accumulation?
Only, yeah, it's a very nice question. Yeah, we were puzzled. So that's right. When we cool the source down, we not only see the velocity come down, but the intensity goes up. That's nice. And yeah, some small part of that is due to population piling down into the low rotational states, but most of it is not. Most of it is genuinely we make more molecules, and we don't, like everything with the buffer gas source, we don't really know why, but we think that actually the pumping, the charcoal pumping, just works better as you go to lower and lower temperatures. And you know, so much about these sources depends on having excellent pumping of the helium. So we think that's probably what's happening.
Any other questions?
Could you elaborate a little bit on the technical challenges with this 17 terahertz laser? So things like mirrors, lenses, windows, I assume don't work as you're used to?
Absolutely. All of those things are a nightmare. Yeah, so the first problem was, you know, getting a laser, and then having a laser. The next problem is, how do you ever see the light? How do you detect the beam? How do you measure the frequency? What windows and optics do you use? None of it is good. So you can use zinc selenide, which, you know, loses about 50% on every single optic. But that's actually the best, pretty much the best that you can do. Mostly we use mirrors. We try to use mirrors everywhere. So, you know, where you would normally have a lens, we would use a curved mirror. Then it's not so bad. But yeah, windows, you know, vacuum windows have to be zinc selenide. The whole thing, yeah, you should not do this. The whole thing is a nightmare.
Any other questions? I have a question. So you mentioned you want to use your molecular clock to trace any variations in fundamental constants. So with optical clocks, we typically look for both the fine structure constant variations and the proton-to-electron mass ratio. I assume the molecule would be more sensitive to the proton-to-electron mass ratio, but there might be a residual sensitivity to the fine structure constant as well. If that's the case, you would need 3 clocks to find out variations of the 2 constants. Do you know what it is for calcium fluoride?
The calcium fluoride, the vibrational frequency, I think, has very little sensitivity to the fine structure constant. Yeah, so they really separate very nicely into, you know, ME over MP coming from the molecule clock and alpha coming from the atomic clock. Now, of course, you still have the same problem, because if you see some variation and you believe that it's real physics, then you still don't know which of the constant is varying. But then, okay, if you have enough of these experiments, in the end, you can figure all of that out. Yeah, and the variation of, so the atomic clocks, they get their variation to ME over MP from the hyperfine structure only. So you get it in, you know, the cesium atomic fountain clocks. They tell you something already about ME over MP. But they, because they're microwave plots, it's only the microwave plots that do that. So they're ultimately limited by being microwave plots.
Look, there's a question.
What other interesting timescales for these variation of fundamental constants you were talking about, like how long it'll take you to get down to 10 to the minus 17 or whatever, for these all these different things you were talking about, what's kind of an interesting place to look for time variation?
Yeah, I think there are two different time scales. So if the constant is drifting, then the expectation is that it's drifting incredibly slowly. We would have seen it by now. Okay, so there, the drift is kind of on the time scale, the age of the universe. So 10 to the 4 seconds is absolutely fine. The ultralight dark matter is supposed to give you oscillating fundamental constants, and the frequency of the oscillation depends on the mass of the dark matter. Almost no bounds whatsoever so far on the mass of the dark matter, and so the frequencies can vary over many orders of magnitude.
I think we can thank the speaker.